ZeeVee and solutions over Coax here at Missenden Abbey. ZeeVee's been in the UK for just over 1 year now, a well-established company in the US, very dominant over there, doing business with the direct TVs and the dish of the States. Effectively, they're the equivalent of the Sky and the Virgin media over here. So we opened an office in the UK about a year ago, and one of the things that, I actually come from the Pro AV side of things. When I started talking to the consultants and particularly the Pro AV guys, there was always a lot of questions and glazing over when I mentioned Coax. So we realised there was quite a bit of work to do with awareness and about what, how great this cable is and what you can do with it. So Coax is everywhere. It's been around for well over 50 years, and one of our speakers will give a detailed history of Coax with some humour a little bit later on. But it's been used to carry video and information around. And quite simply, even today, with the appropriate hardware, it's possible to carry many video channels, internet, and control signals. And when you start looking at it that way and putting together solutions, which is why we're running this event today, you can start having solutions that compete against the traditional, structured cabling solutions, so the Cat5, the Cat6 solutions. So we can replace a matrix switch with Coax and the appropriate equipment. With control, so you can individually control the screens. We can compete strongly against digital signage, where you have a player behind the back of each screen, put the player in the back office, connect it to a ZeeVee encoder modulator, go out to many, many screens, and the cost effectiveness is incredible when you start looking at the numbers there. And against IPTV, that has its place, but if the customer really doesn't need all the features of IPTV, and that's the question to ask, then there are massive savings and benefits to be had by using Coax. So most importantly, it's very simple to install, it's simple to maintain, it's simple to upgrade, it's hugely cost effective, and actually that doesn't necessarily mean that you're not making the same amount of margin selling to your customers. Sell it as a solution and you can still make the same amount of margin. So yeah, that's enough from me. I'll obviously be around in the break. We'll have a break halfway through and afterwards. So I'll be around then, and there's equipment in the breakout area. We've got a couple of breakout rooms showing demonstrations of the equipment, including control and internet over Coax. And I'd like to hand you over to our first speaker, who's Steve Metzger. Steve was one of the founder members of ZeeVee over 7 years ago, and he's our CTO.
Thank you. Welcome, everyone. Thanks for the opening remarks. So we're here to talk about coax and video distribution over coax. And so my job here is to first present how does it all work, what does it mean to distribute channels and video over coax. For some it might be a review, for others it might be adding digital on top of what you might already know about analog television, but we'll just tell you what we mean when we're distributing video over coax. There's a lot of buzz out there these days about new ways to distribute video, IP, and whatnot. The most mature scheme to distribute video is television. It's been around for 80 plus years. It's been under development and refinement, and it still is the most cost-effective way to get high-definition television around from point A to point B. And the main value proposition, which we'll come back to, is televisions come with tuners. Every TV pretty much in the UK these days or in the EU has a tuner in it, so just use it. And that's really where our main value is. So I'm going to go back to the beginning, and we're going to talk about how does TV work, and then how do we build channels and add our stuff to existing TV networks. So this is a TV channel. This is a PAL channel that is constructed of a black and white luma carrier, a chroma color carrier, and an audio. And this is what it looks like in the frequency domain, the energy that's spread out over your 8 megahertz to generate a TV channel. What you do with that is you take a bunch of those and you modulate them up to different frequencies, different channels, so that creates your lineup of TV channels. Just paste them all together. The tuner selects which channel he's going to look at, and he grabs that information off of that. So that's the beginning of time up, 40, 50 years of television, starting with black and white. We added color, and then now we're going digital. But once we go digital and go high definition, there's a tremendous amount more data to carry for the screen. So what we have to do is now start encoding in a much more sophisticated fashion in order to get that much information down that limited spectrum. The earlier developments in the digital televisions, the US started with ATSC, that's the Advanced Telecommunications Systems Committee or something. That was, I believe, the first means to broadcast over-the-air high-definition television. Shortly thereafter, the DVB consortium was founded by 200 members of European, Japanese, and US companies, and came up with DVB-C, DVB-T, the full spectrum of DVB standards. And the reason for doing that, not just doing ATSC, is particularly in Europe, there are a lot of different concerns than we have in the US. Countries are closer together, channels are closer together. DVB-T has one important characteristic that ATSC doesn't, in that you can have multiple transmitters in a relatively close geographic area, and that then helps define the boundary of the TV channel. And it's a better overall scheme than ATSC in the long run. So you are lucky. The bottom line with all of these, where I showed you the picture of the energy versus frequency, is what we're trying to do is cram as much information in that spectrum as possible. So I've got pictures of what that spectrum now looks like for the digital channels, and you can see where you have an 8 megahertz span before, now we occupy it with information from edge to edge, and it's a very efficient use of the spectrum there. They all look very similar, slightly different characteristics. QAM is US for cable, pretty much, and DVB-C. ATSB is what it looks like in the US for US digital TV channels, and then OFDM is DVB-T. And you'll note the sharper transitions and slightly more efficient energy usage for co-FDM. That's coded orthogonal frequency domain multiplexing, for those of you who want to know. But that's what you have here for DVB-T. So the goal of all of these is to get as much information into as limited a spectrum as possible. And this is kind of an eye chart. There'll be a quiz later, so you have to memorize this table. Not really. The goal is to, in a given channel, I've shown what the data carrying capacity is. And then you also have a table that shows for a given type of encoding how much information is needed. And you can see to do a 1080i encode in MPEG-2, it's about 24, 25 megabits per second. And you can see that fits nicely in even a 7 megahertz DVB-T. The DVB-T standard covers MPEG-2, DVB-T2 covers MPEG-2 and MPEG-4 in the difference. So, for example, DVB-T2 channel covering MPEG-4 can carry a couple different programs in a given channel. But the whole idea is those are the channel capacities, those are the bandwidths required to carry certain picture types. But this new form pretty much looks like the old form. We do the same thing. We take those given channels of information, we modulate them up to different positions in the spectrum, and that creates our channels. The important point of all this is, from a frequency and energy perspective, it looks just like the old analog television distribution schemes. So the point here is that if you're planting this into an installation that already has a working RF distribution scheme, more than likely you're not going to have any issues moving directly to a digital distribution scheme. As far as what's where on the planet, you can see early on, the ATSC has adopted North America, Mexico. Part of the northern part of South America still uses ATSC. Much of the rest of the world is DVB-T. South America, Japan, doing something a little bit different with ISDBT. And then China has just come up with DTMB for their own use. But the bulk of the planet is covered by DVB-T at this point. So if you look at what you can do with that piece of coax, lining up all those channels, there's just a tremendous amount of information you're carrying down this. All of these are being carried simultaneously. It's a full TV spectrum. For DVB-C, which is a cable standard in Europe, the common channels, that's 2.8 gig capacity. If you really occupy the full cable, you're carrying 5 gig worth of data down there. So what we're going to talk about is, okay, how do we generate the channel and what do you do with it? I will make one note. Since we're talking about generating a TV channel and putting it on a certain frequency, I think in your packets there's a little card of the frequencies that are used by in the EU for TV channels. One thing that I don't think I highlight in this presentation much is that when you're picking a channel to put your information on, most of Europe converges in this CCR frequency table above channel 21. Below channel 21 is the old VHF days, so there's 7 megahertz. There's a whole mix of the boundaries that the channels are all on. But once you get above channel 21, pretty much all of Europe has converged on this one frequency plan. So it's fairly easy to pick a spot that's not occupied by another channel and just stick your new channels in there. We'll talk more about that in a little bit. One of the benefits here is that coax just massively scales. TV systems, they're designed to go across metro areas. An individual ZeeVee box or run could drive potentially thousands of nodes, depending on the infrastructure you have. But all of the equipment required to distribute television for long distances to large number of nodes is really, really inexpensive. We're talking about RF amplifiers, tens of dollars, 10, 20 pounds, worst case. Splitters, it's a pound or two a piece, if that even. And then wired. So if you don't require amplification, this is a very inexpensive distribution plant. I'll let you run through the math for all that. It's wide acceptance. DVB-T is everywhere. And the televisions all today, for the most part, have high definition DVB-T tuners in there. What you can look for, particularly here in the UK, Freeview HD, that will ensure that the television tuner is capable of receiving high definition DVB-T transmissions. T2, if it's a T2 capable television, it will definitely receive high definition. A component of doing DVB-T2 is that it does DVB-T as well, MPEG-2, MPEG-4, high def, no problem. In New Zealand and Australia, they have a slightly different logo. Where it gets a little gray is for older televisions. If you see, let's say Freeview, if it doesn't say Freeview HD, potentially it's still a digital DVB-T tuner, but maybe not high definition. It might just be PAL quality. Some say HD ready, and the TV may be capable of taking an HDMI in high definition, but maybe not the tuner receiving a high definition broadcast. But most modern stuff is, you'll see the Freeview HD logo somewhere. I started with saying the value proposition for doing distribution over DVB-T or DVB-C over coax is it's cheap. By leveraging the tuner in the television, you don't require any set-top box at the TV or any piece of equipment there. It's using the tuner that's in the TV. Doesn't get much more cost-effective than that. So a very common way to distribute over here is you'll take an off-the-air feed, simply combine it with the ZeeVee or encoder modulator generated signal into an empty channel location, and away you go. That's it. You've added a new channel to the lineup. Scan the television, and away you go. You've got your content there. Doesn't get much easier for DVB-T. If you have DVC installations, it can get a little trickier because you're merging with another cable provider, and they potentially have their own security scheme or numbering or whatnot. But DVB-T, I don't know, our experience here has been that that's almost plug and play, almost. So how does this work? How do we generate a TV channel? Basically, what ZeeVee does, or any digital encoder modulator, is it takes a source of information, video information, encodes it and modulates to DVB-T or C, generates an RF signal out that can be driven into an existing plant to any connected television, scan the TVs, you're done. What we support today for video sources, you name it, we've probably got it. Component video, computer, VGA, HDMI, PAL, and coming up in the next 2 months or so, we have an HDSDI product coming out. So really any video source we can accept, encode, modulate, and generate a channel. So the steps we do to generate that TV channel, if it's analog, we will have to first digitize it. If it comes in HDMI, it's already digital to begin with. Then we MPEG encode, and that's really where we have invested a lot of money and effort, is the quality of the information and the picture you're getting out depends on how well we do that MPEG encoding. So we do a high def, on the fly, MPEG to encode. And we modulate to whatever standard you need. DVB-C, DVB-T, QAM in the US, ISDB for South America, whatever. We'll modulate to whatever is accepted by the televisions in the region you're going to. Different versions of the product for the different modulation types. Amplify it, send it out. And the key, we've spent a lot of effort working on this, is getting that whole process down less than 250 milliseconds. So the lag is as small as we can possibly make it going through all of this. So really all the functions that happen in a TV station, broadcasting, TV broadcaster, we're doing in the box in one step. There's the more detailed picture of the process, which that should be a bright red bubble because most of our man years of effort at the company have been invested in that. But then we generate all of the bit stream, we split into the I and Q to form a constellation that we'll talk about, which is the encoding of that digital information in a spectrally efficient fashion. And we place it in the correct position in the output channel, amplify it, and away we go. Now, I'm not going to go through all of the ZeeVee equipment to do this, but for each type of video input, we generally have a different product to do this, and then we have different variations of these products for the different geographies and modulation types. But this is in your data pack. You've got a full picture of all the products that we offer there. So that's television in a nutshell and how you generate TV channels. We could go for hours into any one of those areas to talk about encoding or modulation or whatnot. But that's what channels look like, and that's what you're dealing with. What I'd like to do is now talk a little bit about if you modulate a channel, what does it take to add it to a plant that already exists, and what is it, how much effort is involved in making that just work. So once you've identified that you want to use digital video modulation for your information passing, you're going into a site. One of the keys to make this work effectively, just make a diagram of where it's going. Identify the infrastructure, what's already there, if they have an amp and a plant and whatnot. Make a simple sketch of this, because it helps sort out cables and losses and how much energy you have to put in. But it also helps us if you end up having to call us to help you out with a problem or whatnot. Having a picture, we've probably seen whatever problem you're going to encounter, we've probably seen that before at this point. But it's surprising, a lot of folks don't. They just plug it in, and in a lot of cases, they'll just get lucky that this stuff just works. But having a picture, that helps us immensely. It seems obvious, but since we're talking about digital television, it's important to have a digital meter. Anyone who's been doing TV for a while probably has old analog meters. Old analog PAL meters, they're not going to work or give you any useful information in the digital world. They're measuring signal-to-noise ratio and things that really don't mean anything when we're talking about this spread spectrum signal for digital TV. They can actually be misleading because they'll give you a number, but depending on the meter and how they're measuring, that number really has no meaning in the digital world. So it's important to have a good meter that measures MER. MER is the metric that tells you how good is the digital TV channel going down through your plant. I've shown a SatLink meter. There's tons of them out there. They're not that expensive these days. If you're going to do installations like this, worthwhile investment. It'll pay for itself in no time. So when you're generating these signals, what you're doing is you're taking an RF signal, you're splitting it to an incident and quadrature wave, and then you're creating what we call a constellation. And this constellation has points on it. We won't go through this, but basically, each point on this constellation represents a group of information, bits of information that form the symbols that then go back and form the video. So this is, when we recover the information off the wire, we create this constellation. Now, in an ideal sense, this constellation would just be a series of points. But when you transmit it through real wire in the real world, you get distortions and phase changes and going through connectors and whatnot, and then it ends up being a fuzzy block of things. So what MER is a measurement of the average distance away from the ideal point that your actual point is. So in a perfect world, I would have these dots all perfectly aligned. In a real world, they're sort of fuzzy. MER is a measurement of how fuzzy are those dots, which ultimately translates into how good is the signal, how well did it get down the wire. You don't have to worry about any of this math. All you have to know is what are the numbers that mean anything at the end of the day. And I'll tell you what good and bad MER is. But an important note is MER never improves through a plant. It doesn't get better when you amplify it. It doesn't ever improve. It only degrades from the source going out. So it's at its best point when you exit the equipment. When we ship our equipment, we test to an MER of 38, 39 dB MER going out the door. That's pretty much the top of what reliably test equipment will measure, and that's what we set it to. The minimum that can be received at a television doing DVB-T tends to be in the mid-20s. So below mid-20s, TVs are going to start getting errors that the protocols can't correct for. It's a fairly robust scheme in that there's a lot of forward error correction that's applied to this so that it can tolerate a lot of bit errors and still recover the signal. But once a digital signal hits a certain threshold, it just drops off. The picture's going to start getting blocky. You'll see that. So DVB-T, generally mid-20s, no problem. DVB-C, it carries more information. There's more bandwidth in that channel on that graph, so it's more sensitive to error. 29, 30 dB MER, that's about, that's comfortable. Below that, you'll start getting some uncorrectable errors. But when you go through a plant, an amplifier degrades the signal. It improves the amplitude, but at the price of MER, because you're going to see some distortions going through that. Any amount of wiring, connectors, whatever. So just be aware of that. If what you're playing with is DVB-T, you know, it's remarkably robust, and we have very few problems over here. In the US, running QAM, you know, we start at 39, and TVs start to bulk at you know, in the mid and upper 30s. So we really do have to manage that quite closely. So like I said, you know, DVB-T is a very robust scheme. T and C actually are better. But when you go into a plant, you're going to look at what channels already exist there and, you know, use your meter, find an empty location, put your channel in that position. One thing a lot of people don't do, which can be very important, is take a look at the spectrum. You're taking in, potentially, if you're merging with over-the-air channels, you've got an antenna on the roof, that's picking up anything in the area. It's going to pick up police radio, it's going to pick up marine radio, anything there, compressors, whatnot. So, you know, do a scan and see, is there a recognizable spike that might be sitting on a channel that you want to occupy that's just environmental? You know, you go into a cruise ship, they've got a certain type of computer system or whatnot. There might be a spike sitting on a channel. It is impressive the number of problems we've seen where folks don't do this. They'll just pick what they think is an empty channel. They'll put their channel there. They'll have problems. It's really hard to figure this out after the fact. We had won the Baltimore Orioles Stadium, Camden Yards in Baltimore, Maryland. They had problems they were having with channels that would go all blocky during games and only during games. And, you know, it was a nightmare to figure out because the spectrum was cleaned. It turns out during the games, the handheld radios that the security guys used, which not during games, they weren't using the radios. There was no interference, but it was showing up. It was causing corruption on all the channels. Maddening to try to debug that, but you know, knowing about the environments and the ambience really helps out a lot. So that's step one. Make sure you're going into an empty, unoccupied channel. The next thing is to make sure that whatever you're combining with, if it's over-the-air BBC, that the amplitude of the generator signal and what's there, pretty much within about 2 or 3 dB of each other. TV amplifiers and tuners, they're very good at picking up on channels. They can discriminate a lot of stuff these days. You know, just marvelous circuitry. But you know, 3 dB represents twice as much energy as its neighbor. So there is a point at which if there's a loud talker next to a quiet channel, you're going to swamp and overwhelm his ability to correct for errors and information. So balance the plant at the source. Make sure the channels are within a reasonable amplitude of each other. And then if you're into this stuff, everyone likes to talk about tilt. And tilt is generally seen if you look at a large number of channels, you'll see the amplitude of those channels either decrease or, in some bizarre cases, increase, but most likely decrease over frequency. So your low channels at the low frequencies tend to propagate better. The upper channels tend to attenuate. Now tilt, in and of itself, it's not as big a problem as some people might make out. as long as there is plenty of signal above the noise floor and it's not too radical of a tilt. If you see a large tilt, what that can indicate is that maybe you've got an old plant with wiring from the 60s or 70s that just can't handle the upper frequencies as much. So it'll see a more of a roll-off at the upper frequencies. That can be an issue. You might want to then skew your channel map down as low as possible in the spectrum. And I did mention that you have a CCR frequency map in there. All of the channels below 21 are usable, and you could certainly program our equipment to broadcast on those channels. But then you have to start being aware of where you are, right? Like in France, some of the low VHF channels are 7 megahertz wide on different spacing than everywhere else. You could put us there, but you then have to figure out what the map is. It's just easier to keep it 21 and above. But if you had a plant where you didn't have enough room up top, you could certainly move stuff down into that frequency range. More of a science fair project at that point. More in the UK than the rest of Europe, there's a network ID. So in that digital channel, there are identifiers for saying, this is my originating network, this is the network that sourced the information, and then my originating network that actually transmitted it. The important thing is to keep televisions happy, we, by default, insert the network ID of the BBC. Right? So that way, you get a free view channel over the air. We broadcast with the same ID as the BBC so that it'll merge in the channel plan and TV will accept it. There are certain televisions where if you set your country to the UK, it will not recognize any other channel or any, if you're near the coast, you're getting a French channel, it's going to not allow those to be part of the plan. So you can change that, you can manipulate this. By default, we put in a network ID of the BBC. The rest of Europe, if you set it to Germany and France, they don't seem to be as sensitive, and they generally accept any network and merge them together as part of the plan. It seems to be a UK-specific problem, which is why our default is in the UK BBC's ID. And then you get to setting channel numbers. So I showed those pictures of the frequency and the energy up and down the spectrum. That defines the RF channel location. In your little CCIR plan, you have to start with channel 21 up to 69. Then there's the logical channel number. And the logical channel number, that's what the user tunes into television. So what you want is, across all the channels you're generating, make sure that's a unique number. Now, with the ZeeVee products, you have the ability to manage all of the product on one page. So you can see, not just one box, but whatever boxes are connected together. They'll all show up in one management page. You can make sure that across all of the products, they have a unique number so the TVs don't get confused about tuning. Because you need a unique number for the user to enter in. And that's pretty much it as far as generating channels, making sure they're numbered properly, make sure the amplitude is generally correct, and DVB-T is fairly tolerant of this. And now you generate TV on your plant, carry digital information. So now we get into promoting ourselves and why we're better than everyone else. So we take a great deal of pride in the MPEG encoding that we do. So we're doing this very quick, quarter of a second. We're doing MPEG 2 encoding of HD signals, but it's a full MPEG implementation. There are a lot of competing solutions out there that take shortcuts, but we're doing the real deal in terms of initial frames, progressive frames, bidirectional frames, the whole thing. Everything available in MPEG we've implemented. The goal being to get as much information down a wire in as few bits as possible. So we continue to invest in this. We've got maybe a decade or plus of man years invested in MPEG encode. And we are continually making it better where we've got the full MPEG implementation. The next step is to do exactly what studios do. What a studio will do is they'll do one encode, and then they'll figure out which parts of it gave them trouble, optimize that, and then do a second encode. Multi-pass encoding, it's called. So you get better quality. If there's high motion, they can take shortcuts in the encode and make certain things look better. That's sort of our holy grail of encoding. That's in an upcoming release. So, the point here is that we're continuing to innovate and make our MPEG encoding better. You buy a chipset off the shelf, that's done. It's in the can. What you see is what you get forever. Since we're doing the full effort from ground zero, we can control all that. And because we own the technology and have developed all this, that leads to better support overall. So we've been able to, if someone has a concern, there's a problem, They want to make something look better, they want to add a feature, we're able to respond to that very quickly. We can add it to the code, we can add the features in, we've done it a bunch of times. These are just a few examples that I could think of. I'm sure there's many, many, many more. And I've heard a lot here as I've spoken to people about things they'd like to add. You know, if we've got signage capability we're adding to the box now, and then some folks wanted to add some pictures floating by on a different sub-channel. And said, well, that would be a very easy thing to add, so we'll probably go out and add that. But if you have things you'd like to see it do, let me know. If it makes sense, we can add it to the product. Now, I know I've covered a lot of stuff. It looked like a lot, but in general, this is pretty simple. It's so simple it's scary. That used to be a marketing copy, but it really is. I mean, if you have a plant that already accepts television, and you follow just a few simple rules, adding digital, your own digital channels on top of that is pretty darn simple. Maybe you don't want to tell people how easy it really is when you're out there because you're charging money for it, but it is. Thank you for the time. Appreciate it. Hopefully it's been informative. At this point, I want to turn it over to Jason, who's going to talk about distributed Ethernet over Coax.